Okay, ladies and gentlemen, we are in the home stretch of Chapter 7. We are finishing it off today. We're going to talk about the last section, which is improper integrals, section 7.8. And we already talked about the first part, which were improper integrals of the first kind. So today we do improper integrals of the second kind. So here we go. So this is 7.8 continued, improper integrals. And this is going to be improper integrals of the second kind. So what does that refer to? I'm going to first start with an example. Suppose we have the following curve, y equals 1 over the square root of x minus 1. And this is defined when x is bigger than or equal to 1, strictly bigger than 1, of course. So here's x equals 1, and it's decreasing as x gets bigger. It looks like this somehow. So it's unbounded as you get closer and closer to 1, but there is still a region below it that's above the x-axis, and you can ask about the area problem for this curve. So how do we, now how would we formulate this? Well, it would have something to do with defining something of the following sort, the integral from 1 to 2 of dx over the square root of x minus 1. But how do we make sense of that? Well, I guess the way to do it is to do what we did previously, which is to take test points closer and closer to 1. So you can take a point T and then calculate the area to the right of T, and then let T approach 1 on the right. So we're going to define this in this case as the limit as T approaches 1 on the right side of the integral from T to 2. I'm going to do this integral from 1 to 2. So it doesn't have to be from 1 to 2, but let's do it from T to 2 of dx over the square root of x minus 1. So we are integrating from T to 2. So let me redo this drawing a little bit. Here's 2. Okay, so we are interested in calculating the area. So what we're going to do is we're going to calculate the area first to the right, and then we're going to take T going to 1 on the right. Okay, so how do we do that? Well, 1 over the square root of x minus 1 is x minus 1 to the minus 1/2, and we know how to find the antiderivative of that. That's going to be given by 2 times x minus 1 to the 1/2 power. There's going to be a limit there still. And we have to take this 2 to the x minus 1 to the 1/2 power, evaluate it from T to 2, and then take that limit. So let's evaluate this expression. So if we stick in 2, we're going to get 2 times 2 minus 1 to the 1/2, so that's 2. And if we stick in T, we're going to get 2 times T minus 1 to the 1/2 power, I believe. Okay. Now what happens as T approaches 1 on the right? Well, if T approaches 1, then T minus 1 is getting closer and is a non-negative number that's getting closer and closer to 0. So this is going to 0. And so in the limit, you're going to get that this is going to be equal to 2. So that is an example of an improper integral of the second kind. And so now I'm going to formalize the definition. So here's the definition of an improper integral of the second kind. So there are three cases. So the first case is that f is some function which is continuous on the half open interval from a to b and discontinuous at x equals a. So the previous example falls into that category where a is 1 and b is 2. And then we define, in this case, the integral from a to b of f of x dx to be the limit as t goes to a on the right of the integral from t to b f of x dx. Second case is f is continuous on the other half open interval from a to b, but discontinuous at x equals b. And so we define in that case the integral from a to b of f of x dx as the limit as t goes to b on the left of the integral from a to t f of x dx. So this would be the picture of the curve in this case might look something like this. You'll have a here, you'll have b here, and maybe you have something like an asymptote, and the curve looks something like this, or so it could be like this. Okay, so then the third case combines the previous two cases. If f is continuous on all of AB except at x equals c. So there it's not. So then we define, in that case, the integral from a to b of f of x dx as the integral from a to c. So that's a type 2 integral of the, that's case 2. That's a case 2 case of f of x dx. And then we can take the integral from c to b of f of x dx. That will be a case 1 case. So this is the definition of an improper, all improper integrals of the second kind fall into one of these categories. So I'm just going to do some examples for now, and let's do them. So the first example I'd like to do is the interval from 0 to pi over 2 of secant of x dx. Now the secant, let me first remind you that the cosine curve is the cosine of x is the reciprocal of secant of x, and cosine of x looks like this at pi over 2, it vanishes. So that means the secant curve at pi over 2 blows up. So secant, it looks something like this. So it's going to be asymptotic to pi over 2. So the way we're going to do this is, first of all, note that this is going to be a type 2 integral, and it's the case 2. So this is the limit as t approaches pi over 2 on the left of the integral from 0 to t of secant x dx. Now the antiderivative of secant of x is ln of secant of x, absolute value secant x plus tangent x plus c. So we're going to evaluate that from 0 to t, and then we have to take a limit as t approaches pi over 2 on the left. And so what do we get? We're going to get, if we stick in t, we get ln absolute value of secant of t plus tangent of t. And if we stick in 0, if we evaluate at 0, we get ln of secant of 0, which is 1. And tangent of 0 is 0. So ln of 1 is just 0. This vanishes. Okay, so now what happens as t approaches pi over 2 on the left? Well, what happens to secant of t? Ln of secant t is as t approaches pi over 2 on the left. Secant of t is going off to plus infinity, and ln of something that's getting big is also getting big. The tangent is actually approaching, tangent pi over 2 is sine of pi over 2 plus cosine pi over 2. And cosine pi over 2 is sine over 2 pi over 2 over cosine pi over 2, and that's also going to blow up. So this is blowing up, and this is going to approach plus infinity, so it diverges. Okay, so it diverges. So here's another one, the integral from 0 to 1 of ln of x dx. Notice that in the previous examples, it's very important to have a picture of the graph because you have to note where the function is discontinuous. So in the case of ln of x, that's a function between 0 and 1. It's a function that looks like this. So it's asymptotic to the y-axis. So we're going to define this because it's an improper integral of the second kind. This is a case 1 case. It's the limit as t goes to 0 on the right side of the integral from t to 1 of ln of x dx. Now, ln of x, we actually recall the integral of ln of x dx is x ln of x minus x plus c. This is by integration by parts. I'm not going to go through that calculation again, but now that tells me if I bring down this down, this is the same as the limit as t goes to 0 on the right of x ln of x minus x evaluated from t to 1, and that's going to give me the limit as t goes to 0 on the right of 1 ln of 1, which is 0, minus 1. That's the evaluation at 1. Now we evaluate at t as t ln of t minus t. Okay, so we have to compute this limit. Now, the first term here is a minus 1. The term t goes to 0 when t goes to 0 on the right. We have to know what's going on with t ln of t. So what's the limit as t goes to 0 on the right of t ln of t? Well, we can do this in the following way. I'm going to try to turn this into an indeterminate form. We can convert this into ln of t over 1 over t. And then as t goes to 0, you get an indeterminate form of type minus infinity over infinity. So L'Hopital's rule tells me this is the limit as t goes to 0 on the right of the derivative of the numerator, which is 1 over t, over the derivative of the denominator, which is minus 1 over t squared, which is the same as the limit as t goes to 0 on the right of minus t. And that's going to be 0, that limit. Okay, so this term also goes to 0. And therefore, the limit in question is going to give me a value of minus 1 from the evaluation in the first set of parentheses. So that's the answer to this problem. It converges to minus 1. Okay. Okay, so there's one more type of issue in this section, which is going to be very important when we get to the last topics in the course. It's called the comparison test for improper integrals. And it's for the improper integrals. I'm going to state it only for improper integrals of the first kind. It goes like this. Suppose you have two functions, say g of x, defined from a to infinity, and f of x defined from a to infinity. So there are two functions. And suppose f of x is bigger than or equal to g of x. is bigger than or equal to 0 on the interval from a to infinity. So then it stands to reason that the area under f of x should be larger than the area of g of x. So if the improper integral for f of x exists, the improper integral for g of x exists. And that's the statement of the test. So the test says this: if the integral from a to infinity f of x dx converges, then so does the integral from a to infinity of g of x dx. Likewise, you can state this in the opposite way, the so-called contrapositive way. If the integral from a to infinity of g of x diverges, you think of that roughly speaking as saying the area under g of x is not finite, then the integral under f of x shouldn't be finite either. So that would say the integral from a to infinity of f of x dx diverges as well. So that's the comparison test, and this is the way to remember it in terms of area. So this is the key condition, and these should also be continuous on their domains. Okay, so that's the statement. Let's see how this can be used. This cannot be used to compute an improper integral, but it can be used to determine whether an improper integral may be used to determine whether an improper integral converges or diverges. So here's an example, a simple example. The integral from 1 to infinity of dx over x squared plus 1. Now we actually did this integral, but let's assume we didn't do it. So we can note that 1 over x squared plus 1 is less than or equal to 1 over x squared on the interval from 1 to infinity. So therefore, but moreover, the integral of dx over x squared we saw from 1 to infinity actually converges. We saw that last time. That was our first example, in fact. So that's going to imply that the integral of dx from over x squared plus 1 from 1 to infinity also converges. Okay, so that's an example. So let's do one final example. Here's an example. The integral from 2 to infinity of dx over x minus ln of x. Okay, so now 1 over x minus ln of x, we want to compare it to something. Now, we don't know the answer, but it looks like in this expression, if you take a look at this, you're subtracting off ln of x from x. So this is greater than or equal to 1 over x, if x is bigger than or equal to 2, because ln is a positive number, right, for 2 and larger. So therefore, but now the integral of dx over x from 2 to infinity diverges. We saw that also last time. So that's going to imply that the larger function, the integral of dx over x minus ln of x from 2 to infinity, also diverges. So therefore, we don't actually have to compute the integral. We just need to have some comparison. And so that's it for today. And that's it for chapter 7. We are done with chapter 7.